Hello everyone, welcome back to Dr. Kwan's Gifted Education. Today we are going to explore one of the most fascinating topics in 8th grade mathematics, expressing repeating decimals as fractions. Looking at a decimal where certain digits repeat infinitely, you might have wondered, what is the exact value of this number, or can it be written as a fraction? By the end of today's lecture, you will acquire a powerful mathematical tool to completely control these infinitely repeating numbers in the form of elegant fractions. Let's dive in. First, let's imagine a whole pizza. If we divide this pizza into 3 equal parts and choose one slice, it represents 1/3 of the whole. However, if we actually divide 1 by 3 to convert this fraction into a decimal, what happens? We get a decimal where the digit 3 repeats indefinitely, 0.3333 and so on. We agreed to denote this by placing a dot over the repeating digit, writing it as 0.3 recurring. In other words, visually it is a clean single slice of pizza, which is 1/3, but in base 10 decimal notation, it becomes an infinitely extending 0.3 recurring. They are precisely the same number. This time, let's divide the pizza into 6 equal slices. One slice is represented by the fraction 1/6. If we divide 1 by 6, we get 0.166666 and so on. Notice that the first digit 1 does not repeat, but the second digit, 6, repeats forever. Following our notation rule where dots mark the start and end of the repeating cycle, we write this as 0.16 recurring. Isn't it beautiful that the true essence hidden behind an infinitely flowing decimal is just a simple, concise fraction like 1/6? Now, let's reverse the process. If we are given the infinitely repeating decimal 0.3333 and so on, how can we mathematically prove that it equals 1/3? The core idea is to completely eliminate the infinitely repeating part after the decimal point. Let's set the number we want to find, 0.3 recurring, as a variable x equals 0.3333 and so on. What happens if we multiply both sides of this equation by 10? The decimal point shifts one place to the right, giving us 10x equals 3.3333 and so on. Now let's subtract the first equation from the second one vertically. Subtracting x from 10x leaves us with 9x on the left-hand side. What about the right-hand side? Since the repeating parts 3, 3, 3, 3 and so on, after the decimal point are completely identical, they magically cancel each other out entirely, leaving only the integer 3. 9x equals 3. Dividing both sides by 9 gives x equals 3/9, which simplifies to 1/3. It's an amazing method that turns infinity into something finite. We can solve a slightly more complex case, 0.16 recurring, using the exact same principle, x equals 0.166666, and so on. This time, we need to shift the decimal point to the start of the repeating block and then to the end of the first repeating block. First, to move the non-repeating digit 1 in front of the decimal point, we multiply both sides by 10. 10x equals 1.6666 and so on. Next, to bring one of the repeating 6's forward, we multiply the original equation by 100. 100x equals 16.6666 and so on. Why did we do this? To make the digits after the decimal point line up perfectly as 0.6666 and so on. Now, when we subtract the two equations, the left side becomes 100x minus 10x, which equals 90x, and the right side becomes 16 minus 1, which equals 15. 90x equals 15. Solving for x yields x equals 15/90, and by simplifying it by dividing by 15, we get our final answer, 1/6. Since setting up equations and subtracting every single time can be tedious, mathematicians discovered a powerful pattern. Take a look at the slider and the pattern grid on the screen. 0.111 and so on equals 0.1 recurring, which equals 1/9, 0.222 and so on equals 0.2 recurring, which equals 2/9, 0.333 and so on equals 0.3 recurring, which equals 3/9, simplifying to 1/3. Do you see the pattern? When the repeating block starts right after the decimal point, you write the digit 9 in the denominator as many times as there are digits in the repeating block, and place the repeating digits directly in the numerator. Let's formalize this into a general rule. If the repeating block has n digits, the denominator consists of n 9s. For example, for 0.ab recurring, since there are two repeating digits, the denominator becomes 99, and the numerator is the entire number ab, resulting in ab over 99. Let's look at a very special, profound example, 0.9999, and so on, which is written as 0.9 recurring. If we apply our formula, what do we get? We write 9 in the denominator and 9 in the numerator, which gives 9/9 or 1. You might ask, instructor, isn't 0.999 and so on slightly less than 1? Mathematically, however, no number can exist between 0.999 and so on, and 1, and using our algebraic subtraction method proves it is exactly 1. In short, 0.9 recurring is just another name for the number 1. Let's practice with a slightly longer one, 0.142857 repeating. If you multiply it by a million and subtract, it takes a lot of work, right? Since the repeating block has 6 digits, you just put 6 nines in the denominator and 142,857 in the numerator. If you simplify it, it becomes 1/7. Now, let's take a step back and look at our number system from a broader perspective. What is the definition of a rational number in mathematics? The most important keyword is any number that can be expressed as a fraction. Look at the Venn diagram on the screen. On the left, we have the world of rational numbers, which are numbers that can be written as fractions, and on the right, we have the world of decimals. 1. Terminating decimals like 0.25 or 0.5 can easily be changed into fractions like 25/100ths or 5/10ths, so they safely belong inside the rational numbers. 2. What about today's star? Repeating decimals? Even though they are infinite decimals that stretch out forever, we learned today that every single one of them can be converted into a fraction. Because they can be written as fractions, all repeating decimals are rational numbers. Therefore, repeating decimals proudly sit in the intersection of rational numbers and decimals. 3. On the other hand, non-repeating infinite decimals like pi, which is 3.14159 and so on, or the square root of 2, which is 1.41421 and so on, have no pattern and can never be transformed into fractions. Thus, they live in the outer region, they are decimals, but not rational numbers. Always remember this conclusion. No matter how infinitely a decimal extends, if it has a pattern, a repeating block, it is 100% a rational number. Now that we've mastered the theory, let's sharpen our skills with some practice problems. We already learned about 0.3 repeating, right? If you set it as multiply by 10 and subtract, you get 1/3. Simple, isn't it? Practice problem 2. 0.272727 and so on, which is 0.27 recurring as a fraction. Let's use our fundamental principle. Let x equal 0.27 recurring. Since the repeating block 27 has 2 digits, we multiply both sides by 100 to shift one full block past the decimal point. 100x equals 27.2727 and so on. Subtracting the top equation from the bottom one eliminates the decimal parts, leaving 99x equals 27. Therefore, x equals 27/99, and dividing both by 9 gives the final answer, 3/11. If you use the shortcut formula, you instantly get 27 over 2 nines, which is 99. You can solve practice problem number 3 the exact same way. To get the answer quickly, since the repeating block is 23, which is 2 digits, you can easily solve it as 23/99. Practice problem 4. The fraction 5/6 as a repeating decimal. To convert a fraction into a decimal, simply divide the numerator by the denominator. Dividing 5 by 6 gives 0.83333, and so on. Since only the digit 3 repeats, we place a dot exclusively over the 3, writing it as 0.83 recurring. Practice problem 5. Which number is larger, 0.3 recurring or 0.33? They might look similar at first glance, but writing them out makes it clear. 0.3 recurring is 0.33333, and so on, meaning its thousandths digit is 3. On the other hand, 0.33 terminates, so its thousandths digit is 0, making it 0.33000, and so on. Since 3 is greater than 0 in the third decimal place, 0.3 recurring is larger. Problem 6. It is advanced 1. Calculate 0.123123, and so on, plus 0.456456, and so on. When adding repeating decimals, it is safest to convert them into fractions first. By our formula, 0.123123, and so on, equals 0.123 recurring, which equals 123 over 999, and 0.456456, and so on equals 0.456 recurring, which equals 456 over 999. Adding them together gives 123 plus 456 over 999, which equals 579 over 999. Converting this fraction back into a decimal since the denominator is 999, we get a 3-digit repeating block, 0.579 recurring. Finally, it's time for the final assessment quiz to wrap up what we learned today. Try to solve these 5 questions on your own. 1. 0.7 recurring as a fraction. 1 repeating digit, so the answer is 7/9. 0.36 recurring as a fraction. 36/99, which simplifies to 4/11. 3. 0.12 recurring as a fraction. Subtract the non-repeating part from the total value. 12 minus 1 equals 11 for the numerator, and the denominator is 90, giving 11/90. 7/9 as a repeating decimal. The denominator is 9, so it repeats from the first decimal place. The answer is 0.7 recurring. 5. What is the value of 0.9 recurring? As emphasized earlier, it is the perfect integer one. Today, we walked through a beautiful mathematical journey, bringing an infinitely repeating world into a finite structure using fractions. Mathematics is all about finding order and patterns where there appears to be chaos. Keep these principles in mind, and I will see you next time with even more exciting topics. Bye.